Okay, awesome. So thank you for being here. Thank you for being online. Today we are happy to have Eliza Negrini from UCLA. She's going to be speaking both at UCSD here and also to y'all. So if anything is unclear or audio messes up, let us know. And if you have any questions, you'll have to unmute because chat, that isn't going to work right. So yeah, Lisa is going to be talking about applications of no collision optimal transport. And yeah, take it away.
Okay. Hello, everyone. Thank you for being here, and thank you for the invitation. As I was telling you, I was very excited to come to San Diego. This is my first time here. It's a lovely city. My name is Eliza. Today I'm going to talk about this paper. This is in press in SciMods, the Mathematics of Data Science journal, but you can find an archived version at this link. And we'll talk about no collision transportation maps and their applications to manifold learning. And I have tried to make this talk, introductory enough for everyone to understand, even if you have not used optimal transport before. So what is the optimal transport problem? This was introduced by Monge in 1781 for soil transportation problem. And around that time, Monge was with Napoleon in Egypt. And so they were surrounded by sand and they had to move a lot of stuff around. So the goal is, how do you move a pile of sand into a hole of the same volume in the most efficient way? So in the laziest way possible. It took about 150 years for this problem to be casted in a mathematical framework that could efficiently be solved in some way. And this was done by Kantorovich. And his thinking about this was to allocate resources during the World War. And so they were deciding how to move around soldiers in the most efficient way instead of elsewhere. And this gave rise to the linear programming, which eventually won the Nobel Prize, Kantorovich and Koopman in 1975. And then the field evolved into many more applications. I have a list later on, and there has been a lot of interest in studying the theory of this optimal transport maps in terms of how they relate to PDE problems. And there's been two fields, Matteo Villani and Figali, about this topic. So it's a great field, and it's still evolving. Okay, so why I like optimal transport, and where have I used it and where people have used it before? There are a ton of applications of this field in economics that was the justification to come up with it. And then industrial engineering, PDs, like I was saying before, a lot of field medals in there, a lot in two, which is still a lot for that. Geometry, imaging, and then today I'm going to talk about machine learning and data science applications specifically. If you look at the literature on deep learning and data science, there has been a lot of interest in generating distributions from data like that and how to train them using optimal transport. I won't talk about that today, but it's a great application as well if you're interested. Okay, so in the problem I'm going to talk about today, our interest is to learn using distribution. So we want to work with data that come in the form of a distribution, and there are many data sets that we have, or that I have used before in my life, and probably many of you have seen before, that can be seen as distributions. And here are some examples. Say images. This is the MNIST data set, handwritten digits. You can just see an image as a distribution by taking each intensity of a pixel, dividing by the sum of the intensities, and then you get the probability of that pixel. And this is another example. If you have a text, you can look at it as a bag of words and then count the words, count the frequency, and interpret that data set as a distribution as well. And then people have used gene expression data sets and interpreted these as distributions. Now, I'm not an expert on this, but Caroline Musmuller, that was here, before she was more an expert on this kind of topic as well. So the reason why we want to interpret data as distribution is because optimal transport can give a natural geometry to compare distributions to each other. And it's really powerful when the point-wise information may not be representative of your data set. Think, for example, of a chaotic system where each point in the time series may be corrupted by noise, and you may get very different trajectories if you change the initial conditions a little. Point-wise, you don't get many information, but if you look at a very long time trajectory for the Lorentz system, you will always get the butterfly distribution-like shape. And so instead of looking at one pixel at a time, we want to look at the whole thing as a distribution and capture what's going on there. So an optimal transport gives us a natural way of doing so. The problem I'll look at today is in the field of unsupervised learning. The idea is given n distributions, mu I to mu n. We will assume they're absolutely continuous for the theory, but we want to discover the underlying structure or patterns that show up in this data set. For example, a classic unsupervised learning problem is how to cluster a data set. For example, the missed digits. Can you cluster all the sevens together and all the ones together and so on? And we do want to do one can do that with distributions as well. And specifically today, we'll talk about manifold learning, which is based on the idea that a high-dimensional data set likely can be represented in a low-dimensional space. Can we find this low-dimensional space? And this is an example. So we have the Swiss roll. This is a three-dimensional, like, curved up ribbon, and the underlying hypothesis or the manifold hypothesis is this three-dimensional shape is actually a two-dimensional object, but you're seeing it in a three-dimensional space because it's curved up. Can we study these data points and the distances between these points and unroll this Swiss roll into a two-dimensional data set? So finding the true underlying dimension. And we want to do that in a way so that points that are closed on the Swiss roll will remain closed in the lower dimensional representation. So for example, red points should be close together, blue points should be close together, but red and blue points should not be close to each other on this representation. And in this application, instead of looking at points, we'll look at distributions as our points. The main issue here is to do this kind of studies, one normally has to compute possibly all the pairwise distances or many of these pairwise distances between 2 points, like 2 red points. They have to be close, but you need to know what close is. So you measure the distance. And using Wasserstein distance directly to compare two distribution requires solving an optimization problem that can be very expensive. And so the goal of this work is, can we use instead a much cheaper way of computing a distance between two distributions that summa is not optimal, is not the optimal distance, but is close to being the optimal one, but costs like a fraction of the computational cost. Okay, and these maps were first introduced by Nurbekyan, my collaborator, Jan-Antoine and Aberman in 2020, in which they gave some existence theorems about the properties of these maps. But they never applied them to manifold learning and data science problems like this. Okay, so today I'm gonna use the Monge formulation for the optimal transport problem. And as I was saying before, the motivation behind the Monge formulation was moving to find the most efficient way to move a mass into all of the same volume. So you want to move the distribution mu into the distribution mu by minimizing the work that you do by doing that. And so the work you can imagine being the, you take up some sand, and what is the distance that you walk to get to the hole where you want to drop the sand in, and you want to minimize the work that it costs you to do that movement. In a from a mathematical point of view, this means I want to find a map T from RD to RD that minimize the cost or the work to move the distribution mu into nu. And this is equivalent to finding the infimum for all these maps of this integral over here. And so there are maybe two things to notice. This condition is a mass conservation condition, so you are not dropping sand on the way. And this is what makes this formulation really hard to solve, and how the control formulation made this problem actually treatable in an easier way. And then the second thing is, what cost do we choose to describe that we use in this formula is normally the L2 norm. And if you use the L2 norm, then the minimum is known as the 2 Wasserstein distance W. Okay, so this is a summary. Okay, so this formulation gives you a way to compare two distributions to find the distance between each other, but as you can see from this, you have to find the infimum of those integrals, and that can be extremely expensive to do in practice. However, there are many pros of this optimal transport distance. There's been a lot of interest in studying its properties, so we have good understanding of the theoretical properties of these distances. W2 defines a distance and Riemannian structure on the probability measure, so we know how it behaves. And then it is extremely sensitive to geometric features of the measures being transported. And what we'll show today is that the optimal transport metrics can capture translation in an image to a translation. They can describe it exactly. So the optima between translated measures is the translation. And I'll show you a proof later. Well, the theorem later about this. And this connects back to the example of the chaotic trajectory. So if you can look at a distribution instead of just a point, you can capture geometric features of your data much better. Okay, so what are the cons? Optimal transfer maps are very expensive to compute because they require a global optimization. They require solving that minimization problem. And if you think of having n distributions that you want to compare, that's n choose 2 optimization problems that you have to solve. So our goal is to use instead something that doesn't require as much. So can we come up with a transport-like map and a distance that are cheaper to compute but retain some of the optimal transport properties? And then once we have those, can we use them effectively in learning tasks? And do they give us some gain over Euclidean distances? And are they as good as optimal transport distances for certain problems? Okay, and so we haven't been the first people to look into this. There has been a lot of study on how to make the optimal transport problem easier to solve, or finding approximate maps for the optimal transport map. So the first one is linear optimal transport, in which we embed the space of distribution in an L2 space. Basically, one fixes a reference measure. So if you want to compare n distribution, you fix a reference one, and then you do the expensive optimal transport distance between your n and your reference. So you only do the expensive optimization n times instead of n choose 2. And then you now have an embedding in L2, and you can just compare two distances using the distance from the reference. And then there has been a few more works in which you have theoretical guarantees as well about commutative distribution transform. This is LOT, but in one dimension, random CDT, CDT in higher dimensional, using sliced Wasserstein distance, no collision transport maps. These were introduced by Levon, and this is what we'll use in this talk. And then there has been a few works on learning from this data and doing manifold learning using optimal transport map. And this was one of the papers that inspired that work as well. Okay. So, and one thing that I forgot to say is, well, it's written here, in this paper, they use directly optimal transport map to do the embeddings. And so the natural question that came to our mind was, if we use instead our no collision maps, can we get as good results as this one? Because this one used the true optimal transport distances. Okay, and so inspired by the Wasserstein isometric mapping paper and by their linearized version by Alex and Caroline and actually you're first. Sorry, not in this order. We wanted to prefer manifold learning using MDS, but on no collision features instead of optimal transport features. And so I'll show you results for that. What we show theoretically is that no collision distances can capture accurately dilation and translation, but they cannot capture rotation. And these the equivalent of these theorems are true also when we use optimal transport maps and linearized optimal transport distances. So I'll show you the theorems and examples about this. And then I have later on a few examples about MNIST, clustering of MNIST digits as well. Okay, so now what are no collision transport maps? They are maps that satisfy these two properties. The first one is the no collision property that says if you have two masses and you move them on a straight line in the unit of time with constant speed, they will not collide on the way. This is the no collision property. And then the second property is the half space. If you have two masses on your domain, you can find an hyperplane that separates them, then an hyperplane that is parallel in the codomain will separate the images of these two masses. Okay, so these are the two definitions that define no collision transport maps. How do this map relate to optimal transport maps? From now, it's not yet clear. But there are two theorems that connect to these two ideas. So the first one is by Ambrosio from 2008 that says that when you pick the cost to be the LP norm for p greater than 1, then optimal transport maps will have the no collision property. This property about moving mass on a straight line in a unit of time. Okay, and then if you have a map with the no collision property, then this is equivalent to having the half space preserving property. So this is the second condition. Then one in which you can, if you can separate your two masses in your domain, then you can find a parallel hyperplane that separates the images in the codomain. Okay, and so if we can build a map with the half space preserving property, which is a very simple and constructive property to use, we'll get for free the no collision property, and we'll know that this is a property of OT maps in certain situations when C is an LP norm. Yes.
The no collision property, is that the particles don't collide at all, or do they don't, like their paths don't cross?
When they go at the same time, they don't collide. If one goes first, then
okay, so that if they pass each other, like if they end up on opposite sides of each other, that still satisfies this no collision.
They don't leave at the same time.
Okay.
They don't embed at the same point.
Sure.
Yeah,
okay.
Exactly. Great question. Yes. Okay, so the connection is this no collision property is a property of optimal transform maps. And if we can build maps that have the half space preserving, we'll get the no collision property for free. And so in fact, the way of building in practice these maps is to build a map that satisfies this. Okay, so how do we do this? And in the paper, you can see the whole like theoretical construction with much more detail. But for today, I'll show you pictures because I think it's easier to understand. So we consider two distributions, mu and nu, on a probability space. We define our starting domain to be this purple square for both. And then we want to impose the half space preserving property. So the first thing we do is we choose a slicing direction, S1. In this case, the first slicing direction is vertical. And throughout this paper, we only use vertical and horizontal slicing directions. And this is very related to trees in computer science. There has been a lot of studying in how can you do random projection trees. Specifically, that is possible, but we have not looked at that in this paper. But okay, so we pick a slicing direction and we find an hyperplane that divides our first distribution mu, this 0, into two parts that have the same mass. In this case, it was like about 14. And then we do the same in our distribution mu on the distribution we want to compare with. And this happens to be 14, but it may not be. Depends on where where the mass is. So then you do it again. You decide you now slice horizontally. From each of the two leaves of your construction, you find where to cut so that you have half of the mass on the top and on the bottom, so 1/4 and 1/4. Same on the other side. And then correspondingly, you do it for the other distribution, and you can see that now the cuts can be different depending on the distribution. So here is about 13, and this is about 16. Okay, and then you keep repeating this process a certain number of times until you end up with 1/2 to the n leaves that have all the same mass. Sorry, with mass 1/2 to the n. All right, so for the continuous definition of this map, you take your number of cuts, this slices that we've done to infinity, and the no collision map is the one that respects the partition and matches corresponding leaves. So the top left will go in the top left and so on, depending on how you slice, and preserve the support. In practice, when we actually do the manifold learning, we stop this cut at a certain capital N. So in the discrete setting, we will stop at a certain N. In most of our experiments, low N's were very good, like already like 4 leaves would give us enough information for a simple data set like MNIST. Once you stop, you will have a certain number of leaves of these squares, and to each of them, you assign a feature for that leaf. And you say, okay, for this 0, I say for this top left leaf, the feature is some kind of center. You can pick any feature you want, but it should be representative of your data in this leaf. For example, here I pick the center of mass. They still represent where most of my mass is in the subject I'm interested in. You can also pick a geometric center. That's an option. And the map T in the discrete case is the one that associates the feature on your distribution mu to the corresponding feature in your distribution mu. And so now you see that to measure the distance between these two distributions, this is now an Euclidean distance between this point and this point, plus, if you do it for all the leaves, divide by the number of points, and you get a distance. So these maps, as they are built, and by design, these maps are half space preserving because we are assigning leaves that have the same mass to each other. And so we got a map that now has the half space preserving property, so the no collision property, and so it shares the property with the optimal transfer maps. But obviously, we didn't do any optimization here, so we can't really expect these to be the optimal one in general. However, they are very easy and fast to compute because they only require a median search. You need to search where to divide your mass into at every step. And as I was saying before, these are closely related to building trees in computer science, and there's been quite a bit of work that uses this construction in other applications. Not only they're fast to compute, even though they're non-optimal, they do provide very good approximations of the optimal transfer distance, and at least in the examples that we have looked at. And I'll show you later the distance matrices and how they relate. Okay, and then, the suboptimality is not severe. And then another negative about this is unclear how to pick the correct number in a discrete case. How do you pick the correct number of cuts that you're going to do? And how do you pick the direction of these cuts? Yes?
When you go back to so you're right here, you're just picking the basis vectors sort of to generate the directions. There's nothing like this would still all work if I picked just like the vertical line first and then some angle, and then it would just be like, where is this?
Yes. So if you pick, let's go back to yes. So the main point is if you pick say this direction here, as long as you divide the mass in two, that's fine. Then you have to pick the corresponding parallel, here and divide the mass in two. So that's possible.
Similarly on the other side of the zero, in the same direction or the?
No, because these two are independent.
Oh, gotcha.
Now the two leaves are independent of each other. The two main points are they should be parallel because that's in the half space preserving condition. The two hyperplanes I pick. They should divide the mass in two. And then when you associate leaves to each other, you have to preserve the ordering that you use to construct the leaves. So you want to make sure that you associate the top left with the top left, whatever that means when you have not straight lines. Okay, so that is possible. Actually, we're discussing with Alex how that could be done. So yeah, the direction of the cuts is not necessarily vertical and horizontal. Yes.
How much does the direction matter? Do you have any sense of is there some notion of a good direction to choose versus a bad direction to choose, or does it not really matter in the limit?
So in the examples we've seen,
can you get closer to optimal or worse, further from optimal if you choose good and bad directions?
I don't know. I have not tried. I would imagine, yes, that there should be better directions for your data set. Because, for example, I'm thinking if you're looking at rotations, maybe you want to use different angles, right, that capture that you're rotating. But I have not tried. So I'd say, yes, the direction would impact the goodness of the approximation in the discrete case, for sure. Okay, and then, so that was the direction, and then the number is also something that you have to optimize for. If you look at this, when do you stop subdividing? If you go to infinity, okay, then you get some good semi-optimal map. Of course, you can do that. If you don't divide enough, then you're not capturing what's going on in the data. But if you divide every pixel, then you just get Euclidean distances. So there is a sweet spot in the choice of the number of cuts that captures the correct dimensionality of your data set. Which in this case, we have done by cross-validation. We tried a bunch and yes.
It's like another question about, so let's say these are maps from like zeros to fours.
Yeah.
You would again also have maps zeros to ones and zeros to threes, etc. The directions and whatnot do not have to correspond to each other. The map from 0 to 4 and the map from 0 to 3, let's say. Those directions that you post don't have to correspond to each other. Like you're using.
No, I think they should correspond, because otherwise you can be using very different features. Or to compare this 0 to a 1, then you use like a completely different feature.
Gotcha.
Like when you subdivide this specific 0 with vertical and horizontal, you'll always get this. And then you subdivide a 1 with this schedule, then you'll get something for the 1. But then if you use a different subdivision for this 0, then now it's a whole different point in the feature space. So yes, once you pick a scheduling, that's it. Like you stick to that for all of your data sets. Okay, so before we go into the examples, I'm gonna talk about a bit of the theory. So today we're gonna do manifold learning. The idea is that I am given a metric space, possibly in a large dimensional space, X with some distance, T of X. And we want to find a simpler metric space, theta, with the distance of theta, for which the distances in my original large dimensional space are preserved in the lower dimensional space. And for simpler, we usually means some RK, some flat space with a small k. And right. Okay. And what was been done before that inspired this paper was using optimal transfer distances for manifold learning on images, or linearized optimal transfer distances.
Hi, Eliza.
Yes.
There is a question in the chat.
Oh, thank you.
Can you say that, or do I need to read?
Oh, yeah. So the question is, our empty partition avoided segments that have no data feature within. So you can, for those, you can select the geometric centers as your features, because it doesn't really matter where you pick your feature there if there is no information. So that's the way we do it. Generally, yeah, oh, okay, great. Generally, though, we stop before we get empty leaves. Okay, thank you. Okay, so the question is, what happens when we use no collision distances now for manifold learning on images? So what kind of specific problem we'll look at? We are given n distributions, and we build a distance matrix. And then we want to find a lower dimensional space where those distances are preserved. The way to do this is we use a manifold learning algorithm like MDS on multidimensional scaling on this distance matrix. And if you have never heard of multidimensional scaling, maybe an example can be useful. Suppose I give you cities in the US, San Diego, LA, and Boston, and New York, and I tell you the distances between these cities. And then I say, okay, now build a two-dimensional map and put the cities on the map so that the distances are preserved. So basically that's what MDS does. It takes all this, the distances, and builds an embedding where those distances are preserved. And the distance matrix can be, any of those distances from before: optimal transfer, linearized, no collision. Okay, in the experiments, we did two things. We took mu being the uniform measure on a unit disk and considers its translation and dilation. So we looked at, these are our data distributions. These are 128 by 128 images. So in a 700 something dimensional space. And these are associated with vectors in R2, the vector of the translation from the origin to this point, this point, this point, and this point. And then similar thing, you start from a unit disk in unit disk and then dilating. For rotations, we considered ellipses instead and rotated those because obviously if you rotate a circle, nothing happens. And then we tried and find an embedding in a two-dimensional space that captured the translation, dilation, and rotation grids, those vectors that generated these transformations. So we embedded this 700 dimensional space into a two-dimensional one. Okay, so before the pictures, here's the theoretical results that we proved. For all of these results, we assume that distributions are absolutely continuous, and this is a classical hypothesis. And then we showed that translation are exactly captured by no collision distances, but also by optimal transport and LOT distances. So there is an isometry between the translation between two distributions and the translation between two vectors in RD, between the two corresponding vectors in RD. And a very simple intuition of why this is true is that if you have two translated circles like this, and you do even one cut, okay? So we pick the vertical direction of slicing for these 2 points in the high dimensional space, then this half is exactly the translation of this half. And so the translation can be captured exactly by these maps. And a similar thing happens for dilations. We have an equivalent theorem for dilations, and these are all true for OT, LOT, and non-collision maps. And then the picture is the same. You dilate a circle and you get that the dilation is exactly the dilation of the house. Okay, this is all great, but then for rotation, this doesn't work. So none of these optimal transport distances can capture a rotation correctly. And again, like this picture is representative, at least in the no collision space, in the no collision case, because if you have an ellipse that you are rotating, something like this. So now when you cut, you don't get that this half is the rotation of this anymore. And so it doesn't work in this case. So we don't get an isometry in the rotation case for either of these conditions. Okay. And oh yes, the way we prove this is there is a way of computing the distances exactly for ellipses. So we found a counterexample for the ellipse space. And so that in general, you cannot expect this, this isometry because for the ellipse case, it doesn't work. Okay, we are at the examples now. Perfect. So the goal is, given a bunch of images of translated circles, we want to reconstruct the grid governing the translation. And so we compute the distances between the different distribution images using optimal transport, LOT, and collisions. We get distance matrices in those cases and then run MDS to find a two-dimensional embedding. So the first question is, how good are the distance matrices that we obtain? And here is, maybe you can see a little bit, but oh wait, let me move this somewhere else. Oh. Okay, so the first question was, all of these metrics give us the distance between our translated distributions. How do they compare with the true optimal transport distance, which is what we want to approximate? And you can see that all of these methods give us good approximations of the true optimal transport distance for translation. And this is expected because from the theorems for all of these, we got an isometry with the distance and these approximate Wasserstein. Okay, one thing to notice is that so here just to explain, the middle column represents the no collision using center of mass as features. The far right column is the no collision using geometric center as features. If you compare these two, you'll see the center of mass got a better approximation of the distance, which is expected because center of mass captures where the data is in your image. And then the far left column is the linearized optimal transport distance. So all of these got very good approximations. However, what the real power of this method is how fast it is. So in this case, we only used 2 cuts. So n was equal to 2. We had 4 leaves. So this is the time it took when you increase the number of translation points from, I think I started from 4 or 5 up until 40, 45 or 47. With 2 points, this is extremely fast. LOT is also very fast, and it compares with about 4 cups or 5 almost. But then the true optimal transfer distance is the one that takes the most, as expected. We have to solve all those optimization problems. And so now, yes.
So for the LOT, that's faster than I would have expected. When I say that as somebody that ran it, but like, what does that includes the cost of doing the optimization?
Yeah.
For what? For what optimize? Like for linear programming, Sighorn, which?
Oh no, linear programming.
Wow, that's fast.
Yeah, it allows.
You're a better computer than I am. Okay.
Yeah, you run this on the.
Okay. Okay, that's fine.
Yeah. Okay, so the approximation is good. For the distances, it's fast. What does the manifold that we obtain in 2-dimensional look like? Does it look like the true translation? So this is the original translation grid. So these are the vectors that you apply to the circle to move it around in the 2-dimensional space. And you can see that, as expected, all the embedding based on optimal transfer distances, fastmap and LOT, and our no collision can capture exactly the translation up to a rotation. While if you just use pixels, then you don't capture this because you're comparing the empty pixels to each other, and you're losing a lot of information. And we tried a few other manifold learning algorithms like isomap, diffusion. One thing to notice is these are all up to a rotation because MVS works like that. So like the example from the cities that I was saying before, if I only give you distances between points, you may be swapping Boston and LA. As long as their distance is preserved, that's a okay embedding, an acceptable embedding. And so it may happen that you get rotated images like this, as long as the points are at the right distance, then this is an acceptable embedding. Okay. And so for dilation, we also got a similar result that we can reconstruct the dilation grid correctly, and this is different than MDS isomap and diffusion maps that are based on pixel features. Okay. Okay, and finally, this is from our, from the theory, this is expected for rotation. We don't have this isometric embedding. In fact, everything based on OT doesn't work. Note that the fusion maps in this case work, but theory says you can't expect OT to work. Okay, unless, this is like the simplest case. If you're rotating a circle, nothing changes, so all of these work, because it's an obvious case. And then the final examples are on MNIST. So this was a bit outside of the scope of the manifold learning and things that we could actually prove about these maps. But it's interesting to see how these metrics work on real data, simple data. So we tried and do clustering of MNIST digits, zeros and ones, and also to study the stability of this method, we tried shared MNIST digit that they proposed with Alex and Alan. For to see how these measures are stable with respect to changes in the distributions. And the idea is we take these, we measure the distances, and we cluster them, and hopefully we can separate the zeros and the ones. And this is completely unsupervised. So we don't give labels to our methods. So in this picture are the results for isomap for different choices of the parameter k. And for, yes, so we use isomap for our embedding, and then we use pixel distances, Wasserstein, LOT, and our no collision maps. And this was just for zeros and ones. These are colored by their corresponding label, but this was unsupervised. This was just to see if it was clustered correctly. So you can see that no collision maps are able to separate the zeros and ones, and also the others are in a linear fashion, so they're linearly separable. But in terms of time, the OT-based VAS map took the most time, and then it took only 4 seconds for the no collision. And to get these results, we only used 4 cuts. So this was extremely fast. So this was the simplest case. When we use shared MNIST digits, we get slightly, much worse results. But we can see that for these choices of the parameter k, no collision got a good separation of the clusters, even when they were shared. And so this seems to show that the no collision distance is robust with respect to this perturbation of distribution.
What do you mean by shared?
Oh, shared, it means dilated.
Oh, sheared.
Sheared, oh, sorry. Sheared, yes. And not only this works well in this case, but it's also quite fast. But in this case, we needed 8 cuts to get those results. Okay, but this is by no means like an exhaustive ablation study, because you could change many of these parameters and maybe get better results for other methods. So what this shows is that for a few parameters that we've tried in this case is we obtained good results. So this shows the robustness of our metric with respect to this distribution. Doesn't really say anything about necessarily other metrics. Okay, so I'm at the conclusion. So no collision maps are fast to compute, and they attain nearly optimal costs, as I showed you in the distance matrix approximation. We get similar results at other state-of-the-art methods for these specific applications, and they require less computational time. And then there is quite a lot that we could study about this. Is like we discussed before, how do you pick different cuts directions? can you optimize them to minimize the transport cost? Right now, we're not doing any optimization. We could decide to try and optimize this direction in a certain way so that the optimal cost is attained. This would require computing the optimal cost, so it would be computationally more expensive. And then do something about classification, possibly on Cypher10 or more complicated data set. The hard part about this is the backgrounds will really impact where the cat is and not the subject you're interested in. And so it makes it way harder to study. Okay, and then these are some references. I have many pages, I think. Yeah, 4 pages of references, but that's it. Thank you.
Thank you, Eliza. So there's one more question in the chat.
Questions from people here?
Yes.
So when you were showing this, I was thinking about have you thought about like any unbalanced transport relating to this? Because you could do the same game, but it's just